get started then. So what I wanted to highlight was, that I guess this is almost the last part of covalent bonding before we move on to the last section on network bonding or covalent network bonding. So just to bring everything back together again so you can remember. This has nothing to do with metallic bonding, what I'm going to talk about today. It's nothing to do with ionic bonding at all, and it has nothing to do with covalent network bonding. So the stuff that I'm going to talk about now is all in the topic still on covalent bonding. So there's a lot of detail in covalent bonding. We've already talked about the following. We've talked about the idea of sharing electrons. We know that already in the concept of forming a bond of a non-metal with a non-metal. So we know the only way they can get a full outer shell is to share. Unlike a metal and a non-metal, the metal loses, the non-metal can gain. Hopefully everybody's paying attention to this. So we talked about sharing electrons. We've also said that the outcome is that we are forming a molecule. And we've looked at lots and lots of structures of different molecules. We've started to use ChemSketch. We've looked at carbon dioxide, and we've been dealing with methane. We've been pouring water all over the bench, okay, as well. So you've been familiar with these structures already, or should have been. So we've talked about molecules. The next thing that we actually spoke about when we introduced the idea of molecules, we had to remember the idea here of valency. So if you didn't know how many bonds, for example, phosphorus formed in a covalent molecule, then you can't really do much in terms of structure. You can't draw the structural formula for phosphorus. And we've actually had several examples of phosphorus. If you don't know that sulfur can form 2, 4 or 6 bonds, then you might as well take a walk. Okay? Because you can't draw molecules unless you know the valency of all the non-metals in the periodic table. Well, these ones we're going to use. There's only a handful in our version of the periodic table. There's only a couple of chemicals we have to worry about, 8 or 10 in total. Omar?
Why is it sometimes that some elements have different valencies?
Because we said elements of period 3 and beyond have more than 8 in the outer shell. They're not stable, but they can do what's called expansion of the octet. Okay, so if we look at sulfur, just sulfur, as an example, we know that sulfur is in group 6. 1, 2, 3, 4, 5, 6. And to work out the valency for sulfur, the valency for sulfur would normally be, what is the valency of sulfur based on normal octet rules? 2. So we do know that sulfur can form 2 bonds, okay? And that will give it a valency of 2. And that's going to satisfy the octet rule. That'll give it 8. But sulfur can also do this. Sulfur can also form 2 more bonds, which would mean it would have 2, 4, 6, 8, it could have 10 in its outer shell, in theory, and it does. We've talked about things like this. We know about hydrogen sulfide. We know about sulfur dioxide, where it forms 4 bonds. We've also spoken about sulfur trioxide. So it's also possible that sulfur can use all 6 of its electrons in bonding. Okay, and that would give it 2, 4, 6, 8, 10, 12, which is fine. Period 3 can go up to a maximum of 18. Okay? So the reason for phosphorus 3 or 5? Well, 3 is the octet analogy. 5 plus 3 more sharing makes 8. Okay? But it's got 5 electrons in its outer shell. It does exist where it can form all 5. Can use all 5. So we talk about that as being expansion of the octet rule. The expansion of the octet. If I haven't explained that already, that's what it is. It's called expansion of the octet. Where we get things like phosphorus forming 5, sulfur forming 4 or 6. We might as well mark them up here, I guess. So I'll highlight those a little bit more. So these ones here, expansion of the octet. All these ones here, chlorine using 7th. And I think pretty much that's all there is that expand their octet. That's it. There's only a few that can actually do that.
Yeah.
Right? So that's how they form more than the normal balancing the number of bonds. Gordon, yes. Yes, it's not as stable as the normal octet. Okay, so they do exist. And I think I said if I had, say, an example of phosphorus pentachloride, if I had that in a jar and if I opened up the jar, it starts to fume white. It's pretty unstable stuff. Okay, but I can get it in a jar, and it does sit in the jar for a short period of time, so it must be able to actually exist. Okay, but certainly not as stable as a normal structure. Normal meaning octet structure. Alright, so we spoke about valence, we know about molecules, okay, and then we introduced last week the idea of valence, shell, electron, pair, repulsion. That was a big section still in covalent bonding, and we said this was important because that determined two things. It told me something about the shape of a molecule, and it also helped me to determine the bond angle of a molecule. So Vesta theory helped me to determine all those things. An example of all this could be as follows. So if I were to look at, say, just ammonia, so between nitrogen and hydrogen, again, if I'm going to draw the structure, I need to know the valency for nitrogen, and I've got to know the valency for hydrogen. Okay, so nitrogen's 3, hydrogen's 1. And I'm going to draw the structure down here. So when we draw the structure for NH3, we actually now should understand that we do it like that. So nitrogen has used 3 of its electrons in bonding. It's got 5 in the outer shell, 2 are left over. And so I just can't do nitrogen like this anymore, because that implies there's only 3 sets of electrons around nitrogen, but we know that there is a spare pair that are non-bonding, called those non-bonding electrons. And of course, the idea is, according to Vesper theory, these are negatively charged, so they're going to force the other 3 downward. Not that there's an up or a down for a molecule, but it's going to force them away. And so, if this is my spare pair up here, okay, they're going to repel these 3 down into a, what shape is that one? The shape, not the bond angle, trigonal pyramid shape, okay? So it's not a tetrahedral. This is a tetrahedral shape because it has 4 sets of electrons that are also bonded. So this is a tetrahedral shape. This is a trigonal pyramid shape, but they both have the same bond angle, 109.5 degrees. This one, 109.5. So they're almost identical molecules in terms of the bond angle. So we spoke about that when we talked about Vesper theory. Okay? Yes, Ricky?
Whenever you've got different molecules, so all the bonding angles have to be the same.
In what molecule?
Just for example, if you've got like nitrogen, hydrogen, or something else, so all of the molecules have to be on the same bonding angle.
Yeah, so if I gave you another structure with nitrogen in it, let's give you this one. So if I had something like CH3NH2, and I said draw that structure. So if I were to base it around the hydrogen, I'd be doing this, okay, and I would know that that would look like that, CH3 sticking out there, okay, and yes, this structure here, just around that nitrogen, would be the same bond angle as this one. It's always going to be the same. It's got 4 sets around the nitrogen. Okay. This one over here, what would that one be? I've drawn it a bit weird. Let me just redraw that. Okay. If I were to look at just the shape around this carbon, just that carbon there, what shape would that be? Hands up if you can tell me without pulling it out. Tetrahedral. Because it's got 4 sets of electrons. So what I've actually got really is this thing here sticking out from there, okay, but it's still based on 4 sets of atoms, okay, or 4 sets of electrons I should say, 4 groups. So anything like that will form a tetrahedral shape. That's one of the things you've got to get through in ChemSketch. So you can't really give that overall molecule a shape unless you pick on one area of the molecule. Okay? So it's really got two shapes in it. It's got a trigonal pyramid shape here, and it's got a tetrahedral shape there. That's why you can't really give that molecule a shape by itself. Okay? Questions on that one? Somebody look at me like this. Yes?
You know the example that you gave us with this molecule here?
Yep, trigonal pyramid, yes.
But how come that's a tetrahedral? Isn't it similar?
No, this is a trigonal pyramid. Here it is. Okay? And all I've done is this. There it is. Did you see the bonding will change? Nothing changed. Okay? So this is a combination of this area here, which is tetrahedral, because if I hide all these things up here, that's a tetrahedral.
Including blue?
Yeah, including the blue nitrogen. That's a tetrahedral. Okay? But if I look at this, and if I hide those, I've got 1, 2, 3, I've got a trigonal pyramid shape there. Okay? So that's why it's conceptually hard to understand unless you can really see it in 3 dimensions. Hopefully that makes it a little bit easier to see. That was a very good question. Alright, next one. Now, so we should be familiar now with some shapes of molecules. And I haven't gone through in a huge amount of detail, but hopefully people are reasonably clear with that. So we've got Vesper theory. So when we're drawing structures now, those of you that are watching, everybody should be watching at this point. So we're drawing structures, and you should be able to actually name structures. Linear, V-shaped, tetrahedral, trigonal pyramid, octahedral, and trigonal bipyramid. There's 6 shapes you should be able to use. Okay. Now, once we use Vesper theory, and we become familiar with that, you probably see why we're taking some time with this, because it is not something that you'll get on the first lesson. Okay? You need to hear it about 7 times to get the idea, to get the concept. Okay? It only took me last year, and I worked it out last year. Finally got it after 40 years of teaching it. Not really, but anyway, sounds good. Okay, now, so Vesper theory. The next thing on from Vesper theory is something called polarity of molecules. That's where we're going to head in a minute. We're going to look at polarity of molecules. And I don't know if you can remember, but when I showed a video a few weeks ago, and it had a structure for water, and it had a molecule like this. It had water sitting here, and then it had another water molecule sitting up here, and it said there are 2 types of bonds within water. Does anybody recall what they were called? There are 2 types of bonds. There's not the OH bond and the OH bond, that's the same, but within this there are 2 types of bonds currently. That's the charge. So I could put a charge here, that's delta negative, that's delta positive. We started doing that in ChemSketch. Delta positive, delta positive. So they are polar molecules, and Leandro?
So, intermolecular and intramolecular?
Good. Inter and intra, because you copied it down these notes in the video. Okay? So, I had a dot going between these 2, okay, and I said this is called intermolecular bonding. Intermolecular. That's what holds molecules together most of the time. Okay? So intermolecular bonding. The stuff that's on the inside here, and we refer to these bonds here, the OH bonds, that is called intramolecular bonding. Inside the molecule. We've also got other names, okay? This one here, intra, is called primary bonding because it involves the bonding between one atom and another atom. Or I could put down a non-metal to a non-metal type bond. Intermolecular is called secondary bonding, and we can't do secondary bonding until we understand what a polar molecule is. And that's where we're heading. That's the next biggest section for this one unit, still one part of covalent bonding. Okay? We're just sort of at the tip of the iceberg. Alright, secondary. This is how a molecule bonds to another molecule. And that explains things like, why is carbon dioxide a gas? Why is water a liquid? Why is crude oil a liquid but fairly thick? And why does honey stick to itself so much? Why is it really hard to get off the spoon you're trying to work with honey? It's weird. Okay? So those things help us to understand what's happening between the molecules. So all the physical properties, things like whether it's a solid, liquid or a gas at room temperature, whether it's got a high melting point or a low melting point, all that is to do with secondary bonding. So what holds the molecules together? Okay, everybody cool with that? I'm just trying to give you a picture of where we've come from, and now we're up to the point of being able to look at a polar molecule. We're going to look at a real simple one. We're going to start with water. Okay? So, we need to look at two things though. The first thing we need to identify, okay, is something called a polar bond. A polar bond. Okay? Now, going back to previous lessons, if anyone assists us, what's a polar bond? Because there's two of them in water, and you've been using ChemSketch. So what's our polar bond idea about? Ricky? Electrons going between two different elements. That's a bond, isn't it? We need a bit more detail. Good?
So probably one side's positive and one side's negative.
No, that's only in the case of an ionic compound. We don't talk about positive and negative anymore. Leandro?
You have two poles, one which is slightly more positive, the other one is slightly more negative.
Good. What causes that?
What causes this is the difference of electronegativity.
Okay, that's what we need. So, difference of electronegativity. That's always been a lot of time on the periodic table trying to work out which elements were the most electronegative and which weren't. We didn't do that just for fun. Okay, well, it was fun. But we needed it to use, to do foundational chemistry, like the stuff we did on day one is now coming back on day whatever it is, okay, in the lesson. So you have to know now about electronegativity. Let's look at a polar bond. It is simply where we've got atoms of a different electronegativity, okay, in a covalent bond. And I'll emphasise the idea of covalent bond because we do not start talking about ionic compounds. We don't start talking about these things here. These things, well anyway, you know what I'm talking about. Alright, so the sodium and the chloride, they're not what we talk about in terms of polar. We don't say that sodium chloride is a polar molecule, do we? That is bad. Okay? Alright. It's bad because it's not a molecule. It's an ionic compound.
It's a bit slow, sir.
Yeah, no, it's an apple. Apple. Alright, now, so we can't talk about ionic compounds or metallic compounds if we talk about polar bonds because they don't have polar bonds. Okay? They are completely different in their structure. Andrew?
I know polarity is a measure of really the difference of like the attraction, how
Yes.
a atom attracts the electron.
Yes.
And but in an ionic compound, there's just such a great difference
Yeah, we're talking about a total loss of one electron and a total gain.
Exactly.
It's a plus charge and a negative. Nothing here loses or gains electrons.
Exactly. It only differentiates with the time electrons spend at each atom.
Yes. Yeah, that's right. Now, if we look at just an OH bond, this is only part of a molecule, by the way. Of course, you never draw a structure like that because you'd say, Mr. Campbell, oxygen always has a valence of 2. Of course I know that. Okay? But we're only looking at a single bond. Okay? Just one bond in any molecule. Now, we've got to ask ourselves which of the two atoms in the bond has got the highest electronegativity. And of course it is oxygen, you know that. Okay? So what that means then, on average, that the electrons in this bond, and you'll see a video in a minute, from another teacher explaining it, it's probably better than me, but he's also fatter. So he goes, and he says what it means basically is that the electrons spend most of the time around here and not much around there. Lots and lots of time around here, and he says not much around there. Okay? So what that means is that on average, if I were to take a snapshot of that single bond, this side of the bond will have a greater negative charge. The delta means tiny negative charge. Okay? Not a negative, it's a delta negative. So it's only a partial negative. That's what the delta means, partial negative. Whereas, if I were to talk about this, to confuse you completely, okay, this is completely different. I don't use a delta negative there for sodium chloride. It's a full negative. It's a full electron charge. Okay? Full electron. Not lost, not shared, sorry. It's gained. Nothing here is lost or gained electrons. They're still sharing electrons. That means over here, if you can imagine the nucleus has been in the middle of these, that I would see the nucleus of the hydrogen more exposed. What do we find in the nucleus? Protons that have got a positive charge. So what we're actually doing is, if you can imagine, we're sucking the electron cloud towards the oxygen more compared to the hydrogen. That's all it is. So the idea of electronegativity really means that atoms that are electronegative are going to draw electrons towards them. Okay? Question?
How would you write that down if you wanted to write it down? Like, I know that someone asks you to write that down.
Yep.
How would you actually write that down?
You get rid of all this picture stuff, and all you do is you say OH, delta negative, delta positive, polar bond.
Oh, that's it?
So you do it. Right? That's a polar bond. Okay, Lawrence.
You know how at the beginning we learned that different subshells have different shapes?
Yes.
Like S is sphere and all that. Would that be different in this?
No? We're still talking about overlapping of the orbitals. That's how bonds formed.
So the outer orbital is different.
Yeah. So we're talking about add electrons. Okay. Add electrons and overlap of orbitals. That's an actual bond. Okay. But don't get confused. It's a simple analogy. Okay. Here of things that are attracting electrons are electronegative. They have a delta negative end of day. Got it? Alright, some other things that are also a polar bond. So if I'm in a molecule, if I could fit in a molecule, but I can't, but if I was, in this case here, carbon and oxygen. Again, it's not a molecule, it's just one bond somewhere in a molecule, and I'm only looking at that bond alone first. What's the polarity of that bond? In other words, where are the electrons going to be on average? Why? Shannon? It's got a greater electronegativity. How do I know? We go to the periodic table. Oxygen's closer to fluorine. Carbon's in group 4, so oxygen must have a slightly more attraction for electrons. So that means if I had to show the polarity of this bond, that would be delta negative and that would be delta positive in terms of polarity of bonds. Questions? Just for bonds, that's it, that's all we're doing. So I could give you any combination really now, okay? H and C, which is the most electronegative? Carbon or hydrogen? Carbon? Think carbon? Hydrogen? Carbon? Which is it? Which is closer to fluorine? Carbon. So, in theory, got a negative, got a positive. Okay, it's not rocket science. Yes?
So, any molecule that's not of its like own kind is going to be polar, yeah?
Bingo. That's it. It's got it. Well, they're going to be polar, but you've got to work out which has got a positive and which has got a negative.
Yeah. So it's like, if it's like O2,
O bonded to O, same attraction, non-polar. Okay, so what we were talking about just then, okay, was this scenario. Again, it's not a whole structure, it's just an atom bonded to an atom. So if we've got two atoms that are the same, the electrons are going to be right in the middle, okay? That's no polarity. Now how do I show it? Well, I don't put delta positive and delta negative on it, because there isn't any. They cancel one another out. Okay? We call that a non-polar bond. So, non-polar bond somewhere in a molecule. Andrew?
That's a diatomic bond. So mostly when you have a diatomic bond between two of the same atom, there is no polarity present within the molecule.
Yeah, things like hydrogen, oxygen, nitrogen.
There you go.
Okay, yep.
something like ethane has to be polar, yeah?
Ethane, no, we're not talking about molecules yet. We're doing that in about 2 seconds.
Oh, okay.
1, 2. Okay, let's take the idea of a polar molecule one step further, because I haven't quite got there yet. Okay, I know it's a long-winded definition, explanation, but I'm doing it to those people that are a long way away in Brisbane playing soccer. So, all right. Polar bonds. Any question about a polar bond or a non-polar bond? Because if you can't get that, you won't get what I'm going to do next.
What? You know, the one part of the assignment was has explanation of whether actually using this material. What do we specifically have to write in there?
I'm getting to that now.
Or are you doing that?
Get to that now. All right. I'll leave best for theory there. Here is where the molecule shape becomes important. Hopefully, I won't lose you in this explanation, because I'm going to now look at. We just did a polar bond. Now, what we want to do is we want to look at a polar, an example of a polar molecule, and see if we can understand the concept within a polar molecule. The important point is this: it is connected to the shape of a molecule. You can't talk about a polar molecule unless you know the shape. That's why we did Vesper theory first, yeah? So, if you haven't got the shape right, your polarity will be wrong. Potentially. Sometimes it can fluke it, but most of the time it's wrong. Okay. So when I draw a water molecule, and I'll do it again, okay? When I draw my water molecule, I have to know that a water molecule is going to be in the shape of a V, and I know it's in the shape of a V because it's got 4 sets of electrons, can't be linear, these two non-bonding pairs force it down according to Vesper theory. So we know that. That's a given. And we can build a molecule. We've done it plenty of times before. So here's our water molecule. Okay? We know it's a V shape. Well, it's V out that way, it doesn't really matter, alright? But it's 3-dimensional and it's a V-shaped, or bent is the other name we could use to describe that one. So there's our water molecule. Now, in order to determine the polarity of a molecule, step number 1, and I'll write it here, step number 1 is, where are the polar bonds in the molecule? Plural, polar bonds. And that's why I have to do polar bonds first. Because if I don't know what a polar bond is, then I can't work out whether a molecule is polar. Got to do polar bonds first. So, now I'll look at each bond individually. So I've already talked about an OH bond. Here it is. And I know that this is a delta negative, and I know that that's a delta positive, don't I?
Yeah.
Because we know it's a difference in electronegativity. There's no difference on this side, okay? This is an oxygen and a hydrogen, so that's also a polar bond, delta negative and a delta positive. So they're different. Now it gets a bit more complex. Okay? So what I do now is, the next thing I look for in the molecule is something called lines of symmetry. To try and explain it to you. Alright, it's not the only way of doing it, it's just one method. Lines of symmetry. Okay? A molecule of water, hopefully you can see, has got at least one line of symmetry through there. And it's also got another one through there. If I were to split the molecule in half that way, right through there, it's a mirror image. Okay? Right through here, it's a mirror image. Okay? So it's got two lines of symmetry in the molecule. Okay? Now the way that we have to now look at this is using the idea of a vector. Who's done physics and who knows what a vector is? So I have to then jump to another level, like up here somewhere.
We haven't done vectors in physics, we just did expectation.
Okay, who can define for us a vector? What's a vector?
Okay.
Andrew.
It is a quantity with a magnitude in a direction.
Good, force in a direction, that's all it is. Okay, that's it. So when we do a vector and we use arrows to describe a vector, okay, what that tells me, the distance is the magnitude of the force. That would be a big force. That's a little force, okay, but they're in the same direction. Okay? That's what we mean by a vector. Now we're going to transfer polarity, the idea of a polar bond, into a vector. A force in a direction. And it doesn't really matter whether we say negative is the head of the arrow or the tail, doesn't matter, okay? But I'm going to now draw a force in that direction, and that corresponds to a polar bond. And the head of the arrow is delta negative. Yeah? So I'll say that again. All I've done is this. I've taken an O and a H and I've said this is a vector from here to here. Here's the force. And I've given it a distance, which is a polar bond. Okay? And of course all OHs would have the same length. You know that already. Okay? The same force, essentially. And the head is the delta negative. So the head of the arrow, I'm going to point towards delta negative. And I can swap it around, it doesn't really matter. I've got another force in this direction. There it is. Now, I've tried to make it the same force because it's the same bond. OH is exactly the same polarity. Now, here's the hard part. Okay? If I add these two forces together, these two vectors, force in a distance, in a direction I should say, I have to take this one over here and it becomes there. I'll move it over, okay, I'll change colour for that one. So I'm just going to transfer this over to there, that's all I've done, because I'm adding the forces now together, the combined forces. And I'll show you this again in another molecule. I'm just going to do one, I'll do a couple. So when I do that, when I add those things together and I want to find out what the resultant is, or what I get when I add those forces together, I end up with another resultant, okay? And here is my final force if I combine those two. Now what does that mean? What it means is this. It means that if I redraw my molecule of water, here it is here, all it means is, if I look at a water molecule from the outside, that's telling me that somewhere up around the oxygen, the molecule is going to have a delta negative, because that's where all the forces basically located. And down here, it's going to have a delta positive. So then again, I've now combined the two polar bonds together. I've added the net force together. When I do that, I get a force in this direction. So as I've drawn the water molecule, not there's any up or down, we know that. It's moving in space all the time. The top of the molecule, or wherever there is oxygen, is going to have a delta negative charge. And the bottom of the molecule, wherever there is hydrogen, is going to have a delta positive charge. Overall, when I look at the combined effect of those two bonds, I'm looking at a very simple molecule. Water is a simple molecule. Okay. Leandro?
So you're telling me that this, we have two poles in one molecule, and when we add this, we get a net force, yeah, and that the arrow is saying that the top is a negative pole and the bottom is a positive pole, yeah?
Yes, that's right.
But then the net force will imply the overall charge of the molecule.
No, the overall polarity.
Overall polarity of the
Polarity.
molecule. Now, what do we use this thing for?
I'm getting there. I said it, didn't I say at the beginning? That helps us to determine why is water a liquid. It tells me something about the strength of this bond.
So we're trying to understand.
Yeah, we're trying to understand why does one water molecule attract to another water molecule? And it's based on the polarity of the molecules.
This is how we calculate.
This is how we work it out. Yeah. This is behind that. Alright?
I don't exactly understand how you expect us to figure out.
I'll do it again. Okay. Another molecule. Let's have a look at this one. Okay, watching. We'll do carbon dioxide. Now we know already that carbon dioxide is a gas at room temperature. So what does it tell you about one carbon dioxide molecule relative to another one? Are they close together or are they a long way apart? They're a long way apart. Okay? Compared to a water structure, we know that water molecules are always going to be close together. That's why it's a liquid. We know about particle theory of matter. We did it at year 8. We should have done it at year 8. Okay? We talked about solids, liquids and gases and we drew them in a beaker, you know? So a gas, the particles were flying out. A solid, you had a shape here, and a liquid, it took up the shape of the container. So you know all that already, don't you? That's year 8 stuff. Okay, now, back to this, carbon dioxide. The rules are the same. Identify the polar bonds. We're only looking at individual bonds. Happen to be 2 double bonds. Doesn't matter. All we're looking at really is a carbon bonded to an oxygen. That's all we're concerned with. Okay, we're not worried about the fact that it's a double bond. That won't affect the polarity of the bond at all. That's the covalency. You guys watching down the back there. So, if I've got a carbon and an oxygen somewhere in a molecule, which is the most electronegative? The oxygen, there it is. Delta negative, delta positive. So I have to be able to identify the individual covalent, okay, the individual polar bonds in the molecule first. But of course, how did I know to draw it as a linear shape? How did I know that? I'm stepping backwards. How did I know that? Because Vesta theory. We spent like a week doing Vesta theory. Okay? We talked about shapes of molecules already. Well, anyway, we spent a few lessons on it. Okay. Over here. This is delta negative. This is delta positive. This is delta negative. So I'm putting in the polarity of all the bonds. Here's a carbon oxygen and there's another carbon oxygen. Now, let's use the same idea of force. And hopefully now this will help Param understand this idea. So now I have this. The centre of the molecule, we'll say, is sort of there. Okay? I have a force in this direction, indicated by that arrow. It's got a carbon oxygen there. I have got an exact, equal and opposite force in the other direction.
Mr. Kimball, you know how we say we can change the direction of the force in? before in that one, you said we can change the direction of the force.
Yeah.
Yeah, you know, this is from that, it says from hydrogen goes the force goes to oxygen, yeah?
Yes.
Can we change that from here as well?
What do you mean?
You know, even the arrow that points, the head of the arrow is on the oxygen.
This one?
But
Yeah.
the head of the arrow is on the oxygen.
Yes.
What if the head of the arrow was on the hydrogen?
It wouldn't make any difference.
But would it change the direction of the...
Yes, it would. But if you're going to use the idea that the head of the arrow is positive,
Yeah.
it'll still be the same. It'll still be positive here and negative there. Wouldn't change it. But you can't have opposite.
Oh, it has to be the same.
Yeah, so if you're going to use delta positive as being the head of the arrow, that means if the arrow is pointing downward, which it would be, the bottom of the molecule would be delta positive. Okay, let me just finish the carbon dioxide first and I'll do your questions. Alright, so what we have now is, using the idea that delta negative is the head of the arrow, I'm saying that's just where all electrons are sort of gathered. We've got equal and opposite forces. Here they are. Equal and opposite. What happens on sports day when you have the same amount of people, you know, in tug of war, pulling on the rope, and the same amount of people on each side with the same strength? What happens? Where does the rope move? Nowhere. It's one of Newton's laws. Equal and opposite forces, they will cancel one another. So there's no net charge overall. If I add these two vectors together, which is what I'm doing by adding these two markers together, okay? So if this is the head is, this is the arrow. If I add them together, look, same, they cancel one another. There's zero force. So when I do a carbon dioxide molecule, when I actually draw it, we should know that a carbon dioxide molecule is drawn like this, and of course it's got no polarity. So from the outside, okay, the molecule looks like that. It's got no delta negative, it's got no delta positive. As far as one carbon dioxide molecule sees, it's just a blob in space and it's got no charge. So why would this molecule go near this molecule? There's nothing there for it to attract towards that. That's why the carbon dioxide molecules, they float away in space. There's no attraction between those molecules. Yeah? They are in a non-polar molecule.
So will it repel each other? Because you got, I think this is delta, oxygen is minus delta.
You could argue that, Gordon, you could say that because they're delta negative they repel. But we use the idea of non-polar. Okay? Now, water. Let's go back to the idea of water. This thing. I haven't quite finished yet, we'll have to break in a minute. I know it's a lot to take in, but we have to get through the whole thing together. Here's one water molecule. Hopefully you can now see that the water molecule is polar. Because when we add the forces together, that are all the polar bonds, what that means is that now we've got a molecule that's got a delta negative and delta positive. So this molecule here is going to attract another molecule towards it, and which way is it likely to go? Any ideas? Yeah, it's probably going to actually orientate it like itself like this. Okay? Alternatively, we could do it like that. Because this is negatively charged around the oxygen. The bottom of the molecule is positive, so these are going to stack themselves on that. That's how we expect it to be. That's why water is a liquid. Okay? So, if it's telling me that water is a liquid, it's pretty hard for me, I don't know whether you've tried it lately, but it's pretty hard to run in the water, like in seawater. Have you ever tried to run? Like in a pool? Yes. It's a very rigorous exercise. You try and run, and so it's pretty difficult to break apart all of those polar molecules, because you're trying to go against all of that electronegative force that's holding those molecules together. Whereas I can walk through carbon dioxide any day of the week. Yes.
Is that why the only reason, is that why the only way carbon becomes a solid is pressure? Because
What are you talking about?
like carbon, with the carbon, is the only reason why it can become a solid through pressure because bonds don't attract each other.
I know what you're talking about. And I think what you're trying to say is, if I wanted to actually form a solid version of carbon, which is say graphite or diamond, I need to force all the carbon molecules or carbon atoms together, yes. But that's not nothing to do with this, okay? That's different bonding again. That's covalent network. Now, but on that point, he's still under something, no matter how silly that sounded, okay? Because I can turn carbon dioxide into a liquid, but what do I need to do that? No, I need it. I need to compress it. In other words, if I can actually get carbon dioxide molecules, force them together, they will eventually turn into a liquid and they eventually go into a solid, which is dry ice. Okay? But it doesn't happen like in a lab under natural conditions. I have to actually simulate. I've got to really force those molecules together with lots of pressure and lots of force. Okay? Whereas water, room temperature, it's a liquid. I don't do anything. Okay? Because these molecules are already attracted towards one another, they are polar. Okay. Methane. Polar or non-polar molecule? Okay. What are the rules? I always try and use rules in chemistry because it's good for people that are dumb. What? Ready? How many lines of symmetry? 1, 2, 3. At least 3 lines of symmetry in the molecule. At least 3. Okay? At least 3. Now, what are the bonds? Carbon, hydrogen.
Carbon
We had on the board before. I got rid of it. Here it is. So delta negative, delta positive, delta negative, delta positive, delta negative, delta positive, delta negative, delta positive. 4 bonds that are equal in terms of their polarity. What do you know about the shape of a methane molecule? It's tetrahedral. What do you know about all these bond angles? Identical. Now it's very hard to work it out for this structure. And there's 2 ways of attacking it. One way Gordon hit it about a minute ago. If you can imagine that there's vectors going to the middle, 4 equal and opposite, but they're all at the same angles. And it's very hard to do it with this, okay? But if I were to look at that structure, and if you can imagine all 4 forces, and if I add them together, they're going to cancel out. They're all going to end up back in the middle. All the arrows, when I add them together, will actually cancel one another out. But it's difficult to see this one because it's a 3-dimensional idea. It's easy to see with this one, carbon dioxide, not a problem. Alright, I've only got to worry about 2 vectors. This is 4. So when I've actually got to add 4 together, it's way more complex. Now, so when I do that, this methane is a non-polar molecule. And again, methane at room temperature happens to be a gas. Non-polar molecules don't attract one another. Now, the other way of thinking about this is, if I were to look at the molecule from the outside, this is how we conceptualise it. If I were to look at methane from the outside, if it was going to be polar, I would need to be able to see clearly from the outside a delta positive and a delta negative. I'd have to see that from the outside. Water's easy. So if I look at a water molecule, okay, if I come in from this direction, okay, if I was flying in on a spacecraft or whatever, okay, it's going to be delta negative here, delta positive there. If I come from this side, I'm going to see delta positive. If I come from this side, I'm going to see the delta negative charge. Okay? Because I already know the molecule's polar. Not a problem. But if I approach methane from any direction, I'm always going to bump into a hydrogen, and according to that, this is going to have all these delta positives on the outside, so it's not polar, it's just going to be a whole mass of delta positives, if you want to look at it like that. Okay? But essentially, there's nothing there. There's no charge here at all. It's a molecule that floats around in space, just like carbon dioxide floats around in space. They're non-polar. There's no reason for this molecule to come to this one. There's no incentive there. There's no charges on the molecules. No delta charges on the molecules. Okay. Now, any questions before we finish off on that? It's a very complex concept. Very complex. So we're going to go through it again, and I'll put the video up as well. Yes? I'll come and sit down with you in a minute. Okay. What we'll do now, I think we'll take a break and